So now I want to look at this question. What do we do if we've determined a linear model is not appropriate? We looked at our graph and it doesn't look linear. Can we still use that data? Can we still try a linear model? So here is an example that is talking about fish. So we've been put in charge of organizing a fishing tournament, and prizes will be given for the heaviest rockfish. So we have a scatter plot of the length of each fish versus its weight in grams. So we notice that this is very clearly curved, but it's not a linear model. Maybe it's quadratic or cubic or maybe even exponential, but it's definitely not linear. So first type of model that we could be dealing with is a power model. So a power model means that as one linear dimension changes, the area of that object changes with the square. So that would be power because it's squared. Similarly, volume and also weight should go up with the cube of the linear dimension. As your length changes by a certain amount, volume is going to change by the cube of that amount. Basically, geometry tells us that power models work in some settings. So power model basically is y equals a times x to the p, describes that nonlinear relationship. But in that situation, there should be a linear relationship between x to the p and y. And if we know what that power is, we can actually use that to linearize our data. So in this situation, we're talking about weight. Weight is kind of similar to volume in that it's three-dimensional. So a power model of the form weight equals a times length cubed should describe that relationship. So what I did to test that theory is we kept weight the same, but then we went and cubed the lengths. And when I did that, so I took each value from our original list of data and cubed all the lengths, and then graphed that against the original weights, and I ended up with something that looks roughly linear, definitely way more linear than our original data. So that scatter plot is given, and then we also have these computer output for that regression or that analysis. So I can use that now to write an equation for that data. The same way we've done before, we're going to use the same information to draw or write kind of a linear regression equation, but with that cubed function in there. So my y is weight, so I'm going to start with that. So weight, and of course this is predicted weight, equals, and using my output, my constant is 4.066, so that's my y-intercept. My slope is positive, so plus, and then my slope is 0.0146, I'll say 0.015, and then times my x variable, which is length, but now I'll see here I have length cubed, so I'm going to write length cubed. Right, so now I still have an equation. I still wrote it the same way that I did all my linear equations, but I'm just adding in that cube because that's what I was dealing with. And then I can use that equation to estimate or predict a value. So if I wanted to find what would be the approximate weight of a rockfish that's 36 centimeters long, I can basically just plug in to my equation. So 4.066 plus 0.015 times 36 cubed, and then I can use my calculator to figure out what that equals, which is 703.9 grams. So I can use that model. Now this is under the impression, doing it this way is assuming that you know the power. So in this case, I knew or had an idea that it was cubed, so I was able to cube those lengths, that x-axis value, and get something that was roughly linear. But sometimes we may know that it's a power model that works, but I may not know the power. So if I've determined that data changes as a power, I can transform the data in a different way. So if I don't know exactly what the power is, but I still want to try to figure out what that linear model would look like, another option is to deal with logarithms. And this is actually the most common way that statisticians transform or linearize data is by dealing with logarithms. So on a power model, to linearize this data, I would basically take the log of both sides. So I would end up with, log of y equals log of ax to the p. And then what I did from there is just used log properties. This is, algebra 2 stuff, to simplify this equation, and it ends up being something like this. So in that situation, the p is kind of acting as your slope, more or less, not exactly, but more or less acting as your slope. So we have this something that is fairly linear. So you have, a y equals a constant plus a number times an x, so that's kind of like your slope and your x. So we do end up with something that is more or less linear. So if I take that idea and apply it back to my fish data, so that was our original data of length versus weight. So what I did was I took the log of both values of both variables, so the log of the length and the log of the weight, and it ended up with this. So I have log length on my x-axis and log weight on my y-axis, and I can kind of see that that data is pretty darn linear. It's very, very close to that strong linear relationship. On the right, you see a residual plot for log length and the residual, or difference between the line and log weights. And again, I can see there that I don't have any major curved pattern. This seems like a very, very good model. And then down here we have some, computer output that we can use to write an equation. So, question you might be asked, because none of this is stuff that you would do on your own. This is information you would be given. So based on the output, we can explain, why do we know it's reasonable to use this model? So I can say something like, hey, my linear or my scatter plot for log length versus log weight looks very linear. So that's a very good clue that a linear model is appropriate. And then also my residual, my residual plot for log length is no pattern, very scattered. Both of those are really good clue that this is a good model. This power model where we linearize the data is working really well. So part B, we're going to write the equation of that least squares regression line in context. So again, going off of what I have here, my y is now log of weight. And again, this is predicted, equals, my constant is my y-intercept, negative 1.899, plus, because my slope is positive, 3.049 times log of length, because that is now my x variable. So that's my equation, and then I can use that model to predict the weight of a rockfish that's 36 centimeters long, which is what we did before, but now we're using this new model to do that same thing. I'm going to start up here because it won't let me write below this thing. So log of weight equals negative 1.899 plus 3.049 times the log of, and I'm going to plug in, 36. So everything that's on the right side of this equation is something that I can put in my calculator. We're going to assume log base 10 because it doesn't have a number, and that's typically what it is. So we're going to use our calculator and just kind of plug this in. And when I do that, I get, so I'm going to leave the left side as log weight, predicted weight. And then on the right side, when I put that in my calculator, I got 2.846. And then last little bit of algebra that I have to do in order to get the weight by itself, I need to get rid of the log. I'm going to do a little 10 to the action. That's kind of how I get rid of that, because the 10 to the log base 10 is what that is. We'll make that cancel, and all I'm left with is weight, which is what I want, equals, and then it'll be 10 to the 2.846, which is 701.7 grams. Just as backtracking, when we did this before with the other model where we just cubed the x, we got 703.9. So we got something that's fairly close either way. Either way, we're making a similar prediction. This one I think is a tiny bit more exact.